Ana?
Okay, I think we are live.
Nós
Great.
estamos ao live. Bom dia pessoal, bom dia a todos os presentes em mais um ciclo de palestras do Programa de Pós-Graduação em Geodynamics e Geofísica da UFRN. Hoje aqui tenho comigo aqui, me ajudando aqui a Sheila. Oi, Sheila. E a nossa palestrante do dia, deixa eu só finalizar aqui, nossa palestrante do dia, a doutora Catherine Mothram. Hi, Catherine. Eu vou falar um pouquinho em português, às vezes eu falo um pouquinho em inglês, so I'm gonna speak in Portuguese and sometimes I'm gonna switch to the English. And for those non-Portuguese speaker, you guys can, if you have questions, you can write it down in the live comments at the end of the presentation, and then Catherine can answer those. Pessoal, nós vamos ter então a Catherine falar um pouquinho dela. Catherine é professora na Universidade de Portsmouth. Ela trabalha com geocronologia tectônica, petrologia metamórfica, geoquímica, né? E fez o seu doutorado na Open University em 2014, fez pós-doutorado depois no Canadá e também na Universidade da Califórnia, nos Estados Unidos. A Catherine vai falar hoje um pouquinho para a gente hoje sobre datação opa, espera aí que caiu aqui a minha... Um minutinho, gente. Caiu aqui minha página aqui. Vai falar um pouquinho, então, de sistemas cobre-ouro, né? Mineralizações cobre-ouro e hidrotermais, e como é que a gente consegue datar isso aí usando calcita, olhando chumbo em calcita. Então, o tema dela em inglês é Direct Dating of Hydrothermal Copper Gold Systems Using Calcite UPB Dating. So, thank you, Catherine, so much for accepting our invitation to talk here with us today. And the show is yours.
Great. Cool. Well, thank you so much for inviting me. It's really exciting to get to speak to so many Brazilian people. So sorry, my Portuguese is not very good, very shamefully bad. So I will be speaking in English for the whole presentation. Okay, so is my screen sharing now? There we go. Great, yeah. Perfect. Okay, well, thank you everyone for coming to listen today. I know Frederica's just introduced me in Portuguese, but I'll just quickly introduce myself in English briefly. So I am a lecturer in structural geology at the University of Portsmouth in the UK. So I teach structural geology, but my research is really focused on using geochronology to date various different deformation processes. So this started off, I did my PhD working in the Himalaya, looking at deep, ductile, metamorphic processes and using accessory phases such as monazite to date ductile shear zones. So I'm still really interested in metamorphism and the ductile crust, but as well as that, I've kind of worked my way up through the crust into the brittle regime as well. So working out how we can use similar tools to date brittle deformation processes and fluid flow in the upper crust. So I sort of span quite a large geological distance in the crust, but the common theme is working on looking at deformation and geochronology. Okay, so as we all know, faults are really crucial conduits of fluids in the crust. So when we're in the deep crust, we're looking at metamorphic processes, metamorphic fluids, melts, which are coming along fault zones. And then as you work your way up into the brittle crust, faults are really important for facilitating the flow of water, oil and gas, and also fluids which cause minerals and metals to concentrate in the crust. So really understanding the rates and timescales of tectonic processes along faults is what I focus on in my research. And it's got a whole load of different applications. And what I'm particularly interested in is linking the dates of the faulting with the processes. So either the metamorphic processes or what I'm going to be talking about today, which is ore generating processes. So for the rest of this talk, I'm going to focus on brittle faults because that's what I'm working on right now. So I'm going to just do an introduction about how we date brittle faults, so some of the methods we can use, and then particularly the carbonate uranium lead dating method. And then once I've introduced that, I'm going to go into a particular research project that I've been working on in Canada. So traditionally, we've dated brittle faults, sort of older brittle faults in the geological record using cross-cutting relationships. So looking at marker beds that have been off-cut, maybe looking at igneous intrusions, looking at intrusions which have gone along faults. But this doesn't really precisely date when the fault was active. It's a little bit easier if we're looking in the very recent geological past. So sort of during the Quaternary, for instance, we can use maybe exposure dating, something like that, to try and work out when faulting happened. And looking at sort of paleo, seismicity, and that kind of the deposits left in the sediments is something that a lot of people do in the Himalaya and other areas. But I've always been interested in older geological processes, which we can't really date using those kind of methods. So we have to use different methods where we can directly date the fault. And this has traditionally been really, really challenging because the minerals that we typically use for radiometric dating, such as zircon, do not crystallize in the upper crust. They don't crystallize in low temperature fluids very often. So it's very difficult to use those kind of techniques. So I'm just going to outline a few of the techniques that we have been able to use. Some of them are more recent than others. So just at the top here, hopefully you can see my pointer. So illite is a clay mineral which is formed in fault gouge. And illite dating is a very well-established method. So there's two different ways we can do this, using encapsulated argon-argon geochronology or potassium-argon dating. And if you look at particularly the work of people like Ben van der Pluijm and Horst Swingman, they've been using this technique really successfully for decades now to date fault gouge. So this was really one of the best methods we had. But for any of you who know about fault gouge dating, I've only sort of dabbled in it, but it's really time consuming. It's very, very difficult. You have to separate out these really, really stupidly tiny clay minerals. And it can be challenging. So what we've been interested in is how we can develop more in situ, easy, relatively quick methods to date these kind of fault surfaces. So if we look at crystals that have mineralized on the brittle fault surface itself, we could look at different silicon fibers or minerals such as opal or hematite, which sometimes form kind of fault mirrors on the surface. So we can use methods such as uranium, thorium, helium dating for hematite, or uranium lead or uranium series to date opal, which is a relatively recent sort of development. And then silicon fibers and veins are really what I'm going to be focusing on today. So we can use rubidium strontium to date some minerals. There was a paper out in Nature Geoscience this year looking at rubidium strontium dating of silicon fibers. But really what I've been doing is looking at uranium lead and uranium series dating of carbonate of mineralized fault surfaces. And really the point of what I'm going to be talking about today is actually syncing these fault clocks. So looking at different methods that we can use to try and get the same information, because if we can date the same fault with two different methods, we can be more confident in those methods. It helps us understand a little bit more about what the dates represent. It's relatively easy to get a date for something. What is much harder is linking it to a process. So that's really what I've always been interested in throughout my whole geological career. So I'll come back to this later in the talk, but this sort of linking of two different methods for dating the same fault is really the purpose of the talk. Okay, so now what I'm going to do is introduce carbonate uranium-lead geochronology, because this is a relatively new method, so some of you might not have heard of it before. So as you know, carbonate, and calcite in particular, is everywhere in the crust. You get it all over the place. So the fact that we can now, in some cases, date this using uranium-lead methods is really awesome. It's opened up a whole range of possibilities for dating processes, particularly in the upper crust. So this figure just shows a few of these different applications. So we can look at dating, for instance, fossils, diagenesis, cements. People have used it to look at paleoarchaeology and diagenesis in the recent past and linked to sort of hominid evolution. We can look at fluid flow along fractures, which is particularly important for oil and gas, water, other sort of reservoir permeability type things. What I'm particularly interested in is dating faults. So looking at fluid flow and deformation along faults in the upper crust, and then linking that to ore mineralization processes. So we've been able to date carbonate for a long time using isotope dilution methods. And if you're interested in that, you should look at, there's a great review paper by Troy Raspberry in, I think, 2009. So people have been dating carbonate for a long time. But what has recently been a big sort of change in this field is we've been able to date carbonate using in situ methods. So all of the stuff I'm just about to introduce is all in situ carbonate dating, so using laser ablation. Whereas traditionally what we had to do was drill out the carbonate, dissolve it, and use TIMS or multi-collector to date the carbonate. So you needed more material and you lose that spatial resolution. It also makes it a lot more time consuming and expensive. So really in about 2014 was the first time that people started to use uranium-lead in situ methods to date carbonate. So this is a study out of the NIGL lab with Randy Parrish and Nick Roberts, Lee et al. 2014, and they dated an ammonite. So this was looking at diagenetic alteration of an original aragonite cement in a ammonite. So there's been absolutely tons of papers since 2014 using uranium-lead carbonate dating to date various different materials in situ. So this is an example of a study by Nick Roberts looking at vein generation in the Atlantic crust. So looking at sort of basalts and carbonate veins in basalts, and they were able to track the opening of the Atlantic, looking at these kind of processes. Perrin Uriel is one of the people who's really been pioneering looking at using uranium-lead carbonate dating for faults. So she's done some brilliant work on the Dead Sea Transform Fault in Israel, looking at how the fault is kind of propagated through geological time from south to north through Israel, using the carbonate cement in fault breccia, and also looking at silicon fibers and veins. So until recently, there wasn't really many papers using carbonate geochronology to look at ore generating processes. So there's been a couple of papers focusing on some anhydrite, gypsum, siderite, dolomite sort of assemblages in some hydrothermal deposits in Germany. And they were able to date these, frankly, museum specimens. They possibly got them from a museum, I'm not sure, they look amazing, from Germany. And they're able to yield loads of different ages. So if you're interested, I would recommend there's a few papers, and they're able to link those to various different processes. So basically, we can use uranium-lead carbonate geochronology for a whole range of different things. We can look at all sorts of different processes. So it's really a great tool, and it's really great that we've been able to make such progress in the last sort of 5 years. And the reason that we've been able to make such progress is just because basically the equipment is better. We can now do bigger spot sizes on our laser. We have more sensitive machines. And we also have a great reference material, which I'll show you later. So I've been particularly interested in how we can use this tool to try and help us understand deformation processes in the brittle crust. So this is the setup that we use here at the University of Portsmouth. So we have a resolution laser, and we couple that to a high sensitivity quadrupole machine. So we don't have a, it's not something out of the ordinary, it's just a fairly normal geochronology setup. As I said, the big difference over the last few years has been generations of technology in lasers and mass spectrometers, which have meant we can analyze sort of lower and lower concentrations. So the problem with carbonate is it has very low concentrations of uranium. And I'll come on to that probably in a second when I explain a bit more about it. So if we've got a more sensitive mass spec, then we can analyze smaller amounts of uranium. So also the other vital ingredient was developing a reference material. So Randy Parrish, Nick Roberts, Troy Rasby worked really hard on developing this WC1 reference material, which is still the main reference material that we use for carbonate geochronology. So we need to have a reference material that we know what the age is, we know how it sort of behaves in order to be able to date something. So before WC1 was sort of characterized, we didn't have any carbonates, and that made it really hard to know whether the dates we were getting from the carbonate were correct. Carbonate geochronology is slightly different from doing something like uranium, lead, zircon, because carbonate contains a lot of common lead, and I'll explain that in a slide in a couple of minutes. Because of that, it means that we can't use carbonate as a primary reference material. Instead, we have to use a synthetic glass. So most people use either NIST 612, 614 as sort of a primary reference material that they normalize all their data to. And then we do a secondary correction based on WC1 for the matrix effects. So yeah, I can explain in more detail if you want to know more about that later or afterwards. So there are also some other carbonate reference materials. Lots of people are trying to develop more because obviously one is a bit limiting. So there's things like Duff Brown that we use for a secondary reference material. And I know there are lots of different groups working on making more reference materials, which is really good. So just very basics of geochronology. We have to get our material into our mass spec. So that's either via diluting it and putting it in as a liquid, or we can use a laser to ablate it as an aerosol. We then take that aerosol into our mass spectrometer where we measure the different uranium and lead isotopes. So this is essentially how we work out what the age is. So we use the decay constants and we look at the ratio between the parent isotope and the daughter isotope. So uranium and thorium, which decays to lead. As I said, carbonate contains very little uranium typically, so usually under 1 ppm. So that means that it also then contains very little radiogenic lead. So that is what is the main challenge. We're analysing very small amounts of uranium, which go to even smaller amounts of radiogenic lead. So that is the main challenge with carbonate geochronology. The other challenge is that carbonate contains a lot of lead, which is not radiogenic, so what we call common lead. So I'm just going to show you what we call Terra-Wasserberg diagram here. So here we've got the lead isotope, so 207, 206, against the uranium-lead ratio down here. And each one of these ellipses is an individual laser ablation point of a carbonate material. This is actually of a speleothem here. And so you can see that the data is kind of spreading between two different intercept points. So one, which is down here, and this blue line, which is the Concordia line, which shows us how old the material is. So these are dates. So this is actually extremely young. It's 400,000 years old. So we've got very young ages on our Concordia down here. We're getting a mixture between the radiogenic portion of our lead, which plots down here, and the common portion of our lead, which plots up here on the y-intercept. And typically that's about, it should be, if we're looking at the sort of typical lead composition of the crust, the Stacey-Kramer's model, it should be about 0.8 to 0.9, depending on what the age of your material is. So if we are only analysing common lead, if you have very low uranium, what happens is the common lead signal completely swamps the radiogenic lead. And in that case, we would essentially have all of our points plotting up on the y-axis. The reason I'm telling you this is because this is the really big challenge with carbonate geochronology. And it means that just because you've got a bit of calcite that you want to date doesn't necessarily mean you're going to be able to date it. If you've got a zircon, you can pretty much always get an age from it if you have got the right kit to date it. Whereas because of carbonate has got such low uranium concentrations, because it's got such high common lead, and as well as that, there's also a very heterogeneous distribution of uranium and lead within the crystal, which we don't really understand what controls that, means that the success rate for carbonate dating is a lot lower than other minerals. So I've done projects where I've maybe been able to date about 5% of the samples successfully. So I've had 95% failure rate and 5% success rate, which is a bit depressing, really. But I've had other projects like the one I'm going to show you today where I've had a relatively high success rate, probably about 50 to 75% success rate. And so been able to get some really great data. So I've been sort of showing you how wonderful carbonate dating is, but I also want to just put this big caveat in that if you're interested in getting into this, it's not easy and it's not always going to be successful. So it's good to keep that in mind. Okay, so now I'm going to move on to introducing the specific research project that this talk is on. So I've explained to you how we date faults in the crust. So why is that important and how can we link that to ore generating processes? So I am not an expert on ore geology. So I am an expert in geochronology. So this has been actually a new project for me, which is I've learned a lot, which has been great. But just very basically, in an ore deposit, we need to have a source of metals. So that often comes from igneous rocks or magmas. We need to transport those metals usually away from their source, so we can concentrate them somewhere else in the crust. So that is often through melts or through fluid flow, or a combination of the two. And then we need to concentrate our metal, usually in the upper crust, so that we can then exploit that using various different resource methods. So the project that I'm going to speak about today is really understanding if we can use carbonate geochronology as a useful tool to create predictive models for when mineral systems have formed in the crust. So we're interested, carbonate's great because it's basically a sort of paleo fluid flow record. It's a fossilized vein. A vein is just a fossilized fluid. So we can try and use it to understand when mineralizing fluids were active. If we've got a system where there are faults which are important in the mineral deposit, then we can use it to understand when the faults were active. And then we can therefore sort of link between the fault materials and the mineralization to try and understand the overall interaction between faulting, fluid flow, and mineralization. The area that I've been working on for this project is in the Yukon. So the Yukon territory is in the northwest part of Canada. So it is right next to Alaska and just north of British Columbia. So it's just up here. So this diagram is just showing you all the active mining and exploration projects in the Arctic in Canada. So you can see that most of them are concentrated over here in the west and particularly in the Yukon. So it's really great case study area because it's one of the most active mining areas in Canada. And it's also really important for the balance between protecting the environment, the local people in the Yukon, and also the economy. So it's a really interesting place to work. So the Yukon has a pretty complex geological history. So it's part of the Northern Canadian Cordillera. It is an accretionary origin. So I think there are areas in Brazil where you have kind of similar sort of geology, but much, much older. So really this has developed over the last roughly 200 million years, where we've had fragments of different island arcs, microcontinents and oceans, which have rifted off the side of North America and then basically smashed back into North America to form this accretionary mountain belt. So very, very simply, I'm not going to go into this relatively complex history, but we've got the North American continent, then this series of intermontane terrains and basins, which, as I said, kind of were like an accordion. They opened up and then smashed onto the side of North America. And then finally, we've got some more exotic terrains, which sort of form the outboard part of the origin. There was an excellent talk by Dan Gibson on this topic a few weeks ago. So if you're interested, please look that up. So we're focusing on the central part of the Yukon, so in the very north part of the Canadian Cordillera. And this is just a zoomed in map of that area. So we've got Alaska over here. This is part of the Yukon, then British Columbia is down here. So you can see these two big strike slip faults. So we have the Denali Fault and the Tintina Fault. And these are huge continental scale strike slip faults where there's been hundreds of kilometers of movement. It's actually thought that these go all the way down into the mantle. So these are really, really significant structures. And within this central part, so this is the White Horse Trough, there are a series of Jurassic and Cretaceous arcs, which essentially form sort of island arcs and what is called the Yukon Tanana terrain, which is an older sort of metamorphic terrain which was intruded by all these sort of batholiths. And there are large numbers of strike slip faults that have really been probably active since some of these igneous bodies were in place, because they're thought to have controlled the emplacement of some of these sort of continental arc type magmas. And then the strike slip faults have continued to be active. So they've been active at least probably since the Cretaceous, or maybe older, and then they've continued to be active, and the Tintina and the Denali faults are still active today. So I'm focusing on this area here, which is along a structure called the Big Creek Fault, which is one of these strike slip faults, which is parallel to the Denali and the Tintina Fault. So this is just now zooming in again. So we've got the Big Creek Fault here. And the reason that this area is interesting is because there are a series of fairly large copper, gold, porphyry style deposits, which are associated and probably structurally controlled by the Big Creek Fault. So these are hosted in Cretaceous granitoids, and the Cretaceous granitoids seem to follow the trend of the fault, which suggests it's controlled their emplacement. There are mines, so Minto is actually a sometimes functioning gold and copper mine. Casino and Coffee are two other big projects. So this area is active and there is a lot of interest in gold and copper deposits here. So the aims of our project, if you remember right the way back to the beginning of my talk now, were to compare different methods of fault dating. So this was a great place because we could access some fault generated materials to do two different methods. So potassium argon dating of fault gouge and uranium lead dating of carbonate. And then also to try and understand whether there was a link between the faulting, the igneous emplacements and the mineralization in this area. So if I focus in now again, this is a bit of a busy slide, but that's just showing you the local geology of an area which is centered around these revenue and nucleus deposits here. So you can see that the Big Creek Fault has kind of split and we've got this little pull apart basin. So you can see Big Creek Fault South, Big Creek Fault North, and essentially what's happened is we've got a little kind of jog in the system and we've got a little extensional pull apart. In that extensional pull apart, we've had the intrusion of some Cretaceous granitoids, which form the kind of host rock for the deposit. And they're also cut by the fault. So this is a schematic cross section through the area. So you can see we've got two strands of the fault sort of bounding each side of the deposit. We've got Cretaceous granitoids, which sort of host everything. So the lighter pink is an early Cretaceous granitoid, the White Horse Suite, and then the darker colours are late Cretaceous. And it's really the late Cretaceous plutons and dikes and also a diatreme as well. So this is sort of roots of a volcano, which are mineralised. And they're really thought to have probably brought in most of the mineralisation, although it's possibly associated with both of the Cretaceous igneous bodies. So we collected fault gouge from both surface exposures of the fault, although I'm not sure if I've put a picture in here, but most of the Yukon is completely covered in trees. So there are hardly any rocks at the surface, but we did manage to find a few fault gouge sections, largely due to placer mining. So I don't know if you've ever watched these programs about placer mining in the Yukon and Alaska, but there's these huge diggers. They expose the rocks. They're looking for gold, but they also dug up our fault, which was very convenient for us. And we were able to collect some fault gouge. As well as that, we also worked on core from, Triumph Gold is an exploration company which are currently drilling in this area, so we're able to work with them, be based in their exploration camp for the last 2 summers and work on their core, which has been brilliant. So we were working on this section here, which is called the Blue Sky Porphyry Breccia. This is thought to be a pipe which has come up from depth and has potentially brought up all sorts of mineralization, potentially from a deeper pluton at depth. So we're able to collect both carbonate and fault gouge from the samples within the core in this breccia pipe. I'm not going to go into too much the structural data because I'm slightly worried I'm going to run out of time. But basically, we collected loads of data at the surface, and we can see that most of the silicon lines and silicon fibers are oriented parallel to the main fault strands. Then if you just look at this middle stereonet here, you can see that in orange is some veins that we have analysed from the core from the fault core from that porphyry breccia. So these veins are actually not oriented quite what we would expect in a strike-slip system, because for a strike-slip system, we'd usually expect veins to be oriented roughly north-south, in this case, parallel to sigma 1. But in this case, they're slightly rotated. And the reason we think that they're rotated is because within overall this sort of pull-apart system, we think that there's loads of other faults within that pull-apart, which accommodated that sort of extension and also slight sort of movement away from each other. So there are a series of fault blocks which have rotated within that pull-apart, and that's likely what our veins are related to. These are some silicon fibers at the surface. Unfortunately, as I've already said, carbonate dating is a bit hit and miss, and none of the silicon fibers we collected at the surface we were able to date. None of them had enough uranium in, which was quite sad, really. So what we focused on instead was some key questions looking at the timing of gouge formation, and then also the timing of carbonate formation in the fault cores. So this is some of the gouge that we collected. It probably looks fairly similar to some Brazilian rocks, so not very well exposed. It wasn't the nicest looking gouge, but we were able to get enough gouge, and also we were able to characterize this to show that it had a lot of illite, which is the orthogenic clay that forms during faulting. So this was dated by Horst Zwingman and his colleagues over in Australia. And we're able to we're using potassium argon illite dating. Now, again, I don't think I have a massive amount of time to go into detail about this, and I'm also not an expert on it. But when we date clay, we date different size fractions. So less than 0.2 microns, less than 0.6 microns, and less than 2 microns. So I told you it was stupidly small. So typically when we date these different sizes, we get different ages based on grain size. But the key thing here is that we have some distinct ages regardless of grain size. And we think that these are recording individual sort of faulting events. And we've shown this in grey. So I'll just go through it from oldest to youngest. So there's one here which is, so these different colours are just different places in the gouge in the area that we dated. So we dated some gouge from over here, from different parts of the fault strand. So the different colours are just different places along the fault. But there's some which are giving about a 73 million year age, some which are falling between about 55 and 60 million years, and then there's some which are younger, so between 50 and 45. So what we interpret this to mean is that we had orthogenic illite crystallizing at all these different periods, showing that we had fault gouge generation at these different times. So if you remember, one of the points of the presentation and the study was to compare sync geological clocks. So look at the difference between our gouge ages that I just showed you, which are showing a relatively sort of wide range of ages, but with these three key clusters, so 73, about 55 to 60, and then younger than 50 million years. So the next thing we wanted to do was look at carbonate veins and silicon fibers. So as I told you, we were lucky enough to work with brilliant exploration company Triumph Gold, and they gave us their entire core library to look through, which, as you can see, is fairly large and was a little overwhelming. And within this, there is carbonate everywhere in this system. There are carbonate veins, different types of carbonate veins. There's different types of mineralization associated with carbonate. So this is one example of a quartz carbonate vein with pyrite selvages along the edge. This is more of a sulfide vein, but you can see there is also carbonate associated with this as well. This is another carbonate vein with some visible gold within it. So the gold and the copper is in minerals such as molybdenum. There's also molybdenite as well, but the gold is either visible gold, and then there are also minerals like chalcopyrite, pyrite, arsenopyrite, lots of different things that I don't have time to get into right now. The carbonate, as well as being in veins, is also in these kind of vugs. So a lot of this core just looks like there's been explosive sort of fluids, hydrothermal fluids, which have just been smashing through the whole of this area. This is an SEM image showing some of the different minerals. So you can see here we've got a really big bit of chalcopyrite with some other pyrite in the middle. There's some calcite, and then also some dolomite, altered granitoid with some visible gold. And large quartz phenocrysts. This is another example of what some of the veins look like. So we've got really lovely dolomite here surrounding some quartz, big, what looks like later calcite, and then pyrite, chalcopyrite, visible gold. So we focused on looking at some carbonate veins such as this. So these are oriented carbonate veins, which I showed you the orientation before. So they're likely related to some block rotation within that pull apart. And I'm just going to show you 4 thin sections. So these are polished sections which we cut from this one sample. So here we've got a relatively thin carbonate vein here. There's then some pyrite, then a much thicker vuggy carbonate vein. Then we've got other sort of what looks like sheared surfaces through here. And this is all in very much hydrothermally altered granite or granodiorite. So the 4 sections just shown here, so A, B, C, and D, and you can see that they're cutting through those 2 different types of carbonate vein. So in orange is this thin vein here, which has got the pyrite on the edge. So you can see that thin vein with pyrite, another cut through it in section B. And then you can see the much bigger vuggy carbonate, which I've highlighted in blue. So we've got at least 2 different generations of carbonate here. I'm just going to show you now with the SEM pictures to go with them, the EDS X-ray maps. So you can see that we've got our thin carbonate separated by pyrite to the vuggy carbonate. There is molybdenite within this carbonate vein. There's chalcopyrite, pyrite. And if I show you now the vuggy carbonate, there is some minerals like galena, also barite. So all of these carbonate veins seem to have some mineralization associated with them. So now I'm going to show you the geochronology data for this series of sections. So if we focus on that thin carbonate first, the orange one, it gave a really great age of 73 million years. So this is probably the best carbonate sample I've ever dated, because you can see that all these laser ablation points are clustered close to Concordia. So close to this blue line. So that means that they're relatively radiogenic. So we don't have as much common lead in this carbonate. Instead, it's mostly radiogenic lead, which means that we've got a really precise age and it's really great, about 73 million years. And if you remember, that was exactly the same age as our potassium argon data gave us as well for the fault gouge. Now, if we focus on the blue, so this is combining the data from all the sections. So we've got older 73, which I just showed you for that thin carbonate. Then the vuggy carbonate is giving a separate population. There is a bit of overlap, and you can also see there's a lot more common lead here. So you can see it's going all the way up to about 0.84, which is that common lead composition. But it gives quite a nice age of about 60 million years. So there's probably a little bit of spread here, which could be it could be real spread, it could be real geological spread, because there's likely multiple carbonate veins within this. But we've got two clear populations, one at about 73, the other one about 60. So there's different hypotheses which I haven't really got answers for right now, and it's actually sort of the next part of this project is really to link the carbonate with the mineralization in a little bit more concrete way. Because some of the key questions are, is this pyrite sort of coming in with this carbonate bearing fluid? Is this remobilized from some older deposit? So do we have older metal in the system which is being mobilized by carbonate bearing fluids and reprecipitated? It seems likely that this younger 60 million years, that's what's happening, because there are sort of polymetallic mineralization associated with that. So yeah, did the 73 million year carbonate split an older vein potentially? Did it grow in the vein? Is the 60 million years post-dating the mineralization? Probably, but how much is it remobilizing that mineralization? So these are really key questions which I don't have answers to right now. One thing I have done is I've looked at clumped isotopes. So again, I don't have time to go into clumped isotopes, but this is a method of getting temperatures from carbonate. So I've been able to look at the two different ages of veins, and they give two very different temperatures. So the 73 million year age gives a temperature of around 300 degrees centigrade, whereas the younger vuggy carbonate gives a much lower temperature, something like 150 degrees, so, or 120, 150. So even though there might be some slight inaccuracies in those absolute temperatures, the difference is real in those samples. So it's going to be interesting moving forward to use that to try and understand what the role of the carbonate is in the mineralization story in this system. However, let's just focus on the faulting for now, because we're coming towards the end of the time. So you remember that we couldn't date the silicon fibers from the surface of the fault system, but we found some silicon fibers in the core and we're able to date those. And they gave a really nice tie line between radiogenic and common lead at about 57 million years. So I'm going to show you all of that data together now. So on the left-hand side, we've got our potassium argon fault gouge data. So as I said, we've got the different grain sizes of the gouge. We've also got different locations along the structure, but the fact that we've got independent ages which are giving the same age but from different samples, different grain sizes, so if we interpret that to mean that is when the gouge was crystallizing, that is when the fault was moving, it was grinding up the rocks, it was forming clay at that time. And on the right-hand side, these are my carbonate data. So I have this one sample which gives an age of 73 million years, which is exactly the same age as these three gouge fractions. Then this younger age I've yielded from several different veins and also my silicon fiber sample between around 55 to 60 million years, which again corresponds exactly to what the potassium argon ages give us. Then the potassium argon ages go down to younger ages, but I can tell you now that there are definitely silicon fibers which are around the same age, because I've dated more and more silicon fibers now which correspond. So it shows that the fault system has been active multiple times. And that's really what we would expect in a large strike slip system, that it would continue to reactivate and that we might have different fractures, different different parts of the fault system moving at different times, but it's being recorded in both the carbonate and the gouge samples. So going back to some of these questions, so what was the timing of gouge formation and carbonate formation? Well, we've clearly shown that to be crystallizing over several periods. Role of faulting in mineralization, well, it was almost certainly very important, and I will just explain that. I'll go on to the next slide. So there is some rhenium, osmium, molybdenum ages for this system, and they yield ages about 75 million years, which is similar to some of the youngest igneous rocks. So we know for sure that mineralization was happening at that time. And you can see here, this is just a sort of timeline of what all our data shows. We have evidence that there was faulting and fluid flow just at the sort of final stages of igneous emplacement and mineralization. And we really need to drill down into a bit more detail how the carbonate links to the mineralization. But for sure, there is a link between the faulting opening up space for both igneous emplacement, hot fluids. We've probably got mixing, because also these granites are relatively shallow as well. We've got mixing probably of surface waters coming down, mixing with magmatic fluids. We've got massive explosions going off everywhere. If you look at the rocks, they're just, I don't really know what the technical term is, but they are very altered and very fragmented and mineralized. So we've been able to sort of record that early history in our data, but we've also got a long history of faulting, which has happened subsequently, which is recorded both in the carbonate, which are these purple, and then also the potassium argon, which are the coloured shapes. So this is just a sort of little cartoon of showing our pull apart. So we've clearly had faulting recorded in both the carbonate and the potassium argon on the main fault strands at 73. And then we've got these series of younger events which are recorded in different parts of the data set. And some of this is likely related to block rotation in this pull apart, but at the same time as mineralization. And one thing that our data does show, well, it shows that both of these methods yield the same ages, which is absolutely brilliant and shows that we can be confident in both of these methods. And it really shows us that they're probably recording some of the same process, although again, that's something to discuss in the future of what exactly the sort of closure temperature in the uranium lead carbonate system is and how it relates to the potassium argon. But the fact that we're getting the same ages is interesting. And then just the final thing I'm going to say is that being able to date both fault gouge and carbonate is really interesting, because here we can look at sort of seismic processes. So we can look at that mechanical grinding and fault gouge formation, and also fluid flow. And so if we think about sort of the fault valve model, the famous Simpson models, then you can remember that it's sort of thought that sometimes seismic activity sort of allows for fluid flow, which then reduces the strength of the rocks. And so being able to date both of these different processes helps us to able to sort of directly date this kind of fault valve behavior. And in our rocks, the fact that we've got both gouge generation and fluid flow does suggest that when we had seismic periods, that enabled fluid flow, which then enabled mineralization. So there's definitely a link between these. So summary of my project so far: potassium argon and fault gouge dating, carbonate uranium lead dating yield the same ages. We've got mineralization sort of both during this initial faulting, but also afterwards. We've potentially got some empirical support for the fault valve model. And we've also dated this fault for the first time. And this is actually one of the first times that people have directly dated strike slip faults in the Yukon. So it's got fantastic potential for providing some real tectonic constraints for the region. There's loads of work that I've still got to do. So I'm interested in looking at stable isotopes, doing more carbonate dating, really to try and link the mineralization and the carbonate story a little bit better. This work is going to be published in Geology hopefully very soon. So if you're interested in finding out more details, please look it up. So it should be coming out in the next 6 months, I would say. So, and as well as that, I've just looked at this little area, nucleus revenue, but this is a really big fault system, and there's also loads of other mineralized faults in the area. So there's really tons of work to be done. So I'd like to thank Dawn Kellett. She came up with this project and we've worked on it together the whole time. So it's really been very much a collaborative project between Dawn and myself. And thank you so much to Triumph Gold, who let us use their exploration camp. And it wouldn't have been possible without these people. The final thing I want to say is that we've been lucky enough to get loads of Brazilian students in Portsmouth, and I've really loved finding out about Brazil. I'm hoping to go to Brazil soon. So if anybody's interested in sort of developing collaborations or coming over to the UK, please get in touch with us because we love Brazilians here in Portsmouth. So please come and see us. Great, I think I'm done. I don't know if we are going to take questions now. Here we go.
Here we go. Thank you, Catherine. Very nice talk. And we are open for questions. Pessoal, a gente está aberto para perguntas, quem tiver perguntas. A gente tem uma aqui já, foi mandada logo no começo da... we have already one question that was sent in the very beginning of the presentation. So Alberto Ruggiero, he asked, what is the oldest acceptable dating of calcites? And another question, can we date Paleoproterozoic calcites?
In theory, yes. So if there is enough uranium and actually older calcite is better because you've got more radiogenic lead, which has had time to build up. The only problem is that if we're using a Terra-Wasserberg plot, when we get to that part of the Terra-Wasserberg plot, if you're looking at tie line between radiogenic and common lead, it kind of goes right along Concordia, so it becomes more challenging. So you might have to look into using a different kind of plot to work out what the age is. But in theory, it is possible. I can't think just right now off the top of my head of some studies, but I'm sure there have been studies which have dated slightly older carbonate, although most projects have worked on Jurassic to younger carbonate, I have to say.
Okay.
I just looked, there's a question, is it possible to date other carbonate phases such as manganese, barium carbonate, dolomite, uranium, uranium lead dating? Yes, it is. So actually the data I showed you today is from dolomite. So it's definitely possible to date dolomite. I've been interested in trying to see if we can date anchorite. Unfortunately, so far I've not been too successful. So looking at sort of iron bearing carbonates. But I think it might be possible, and I think there's lots of people trying to open up the different types of carbonates that we can look at. The key thing is also reference materials. So if we want to do anchorite dating, we probably need an anchorite standard. Okay, so Raphael's asked about the advantage of using uranium lead rather than uranium series. So they're just different tools for different ages of material. So uranium series, the oldest thing you can date with uranium series is about 500,000 years. So if you're dating silicon fibers on active faults, so I've been using this technique to look at faults in the Himalaya. So they're very recently active, so we can use uranium series dating. And uranium lead dating, the material is just too young, because probably the youngest thing we can date with uranium lead, well, you saw that speleothem I showed was 400,000, but that's a really unique case. Speleothems have got loads of uranium in. The other thing is when we're looking at young material, we need to be worried about disequilibrium. So I probably won't go into that right now, but if you're interested in dating young stuff, you need to look up disequilibrium.
All right. I have a question. I'm interested in how you calculated those temperatures. Can you talk a little bit of that?
With the clumped isotopes. So again, I'm not an expert in this. I worked with another lab for this, but clumped isotopes are looking at isotopologues of carbon and oxygen in the carbonate. And basically the clumping of the carbon and the oxygen within the material, it happens at different ways at different temperatures. So from looking at those isotopologues, they can work out the temperature. Now, the temperatures are worked by some kind of calibration curve. So that's why I said that the absolute temperatures might not be quite right, especially because mostly clumped isotopes are used for sort of sedimentary fluid flow ocean projects, so very low temperature fluid related stuff. So 300 degrees is like ridiculously hot for clumped isotope work. But that difference in my two carbonates is real. So it shows that I've got two different, completely different temperature fluids forming the different age carbonate.
Okay, thank you. More question, people? Mais perguntas, pessoal?
And I think probably in Brazil, there might be some projects where you could use the same kind of approach. So you could look at the relationship between veining and faulting and maybe mineralization using different carbonates. And I think if they were older systems, it actually might be slightly easier, although then your precision on individual ages is also going to be bigger. So you might not be able to relate the processes quite so easily if it's very old.
Mm. So, we're waiting for more questions. Não tem mais perguntas aí. People are very shy in this presentation. I don't know what happens.
I've never met a shy Brazilian person yet. Well, maybe a few slightly quieter ones.
You're biased.
But yeah, as I said, it's been absolutely fabulous the last few years since I've been at Portsmouth, because we have loads of visiting Brazilian researchers. So some people come over for 6 months or a year, or like Shayla come over for their whole PhD projects. So it's been fantastic to get to know some Brazilian people.
It's an amazing place. So I'm really missing Portsmouth now.
Oh, we miss you too, Shayla.
Yeah, I hope I will see you in 2 weeks. Hope so.
In 2 weeks?
Yeah.
Don't go.
That's exciting.
Yeah, I hope, because I don't know if the European Union will accept me. I don't know.
Yeah, there's this thing.
Yeah, they were talking about this yesterday. So let's see.
So it seems we don't have more questions.
Oh, hang on. Someone's asked a question now. Did you date the different zones of the fault? So we did date different strands of the fault, particularly with the gouge dating. So we're able to look at sort of both sort of major parts of that pull apart, and then also some individual faults within. All the faults that we looked at in the core were quite challenging, because I don't know if you've ever worked with drill core, but even if they know kind of which direction it's come from, to try and work out in 3 dimensions what's going on in the subsurface is quite challenging. So some of the faults we dated in the core, we're interpreting to be these kind of little kind of block rotations within the pull apart. But mainly the older ages were from the main part of the fault, but also I got some older ages from within the main mineralization system in the fault core as well, in the drill core. And I think the more material we date there, the more complex the picture will get, because I think there's been a lot of different periods of fault movement in that whole system. It's been active over quite a long time.
Did you try dating calcite from skarns, metasomatic rocks?
I'm not sure if anyone has, actually. I'm sure people have tried. The main problem with skarns is they might be too high temperature, because at the moment, I think there is a temperature limit on carbonate uranium lead geochronology, although we don't understand what that is. But every time I've tried to date anything vaguely warm/hot, like I've tried to date metamorphic carbonate, that has not worked. Everyone I've spoken to who's tried to date marbles, calcsilicates, anything like that, it has not worked. So maybe at a certain temperature, uranium becomes mobile and it just goes out of the carbonate. So I'd be interested to see if we could date skarns. The thing with skarns is you often get things like titanite and garnet in them. And I know people have done garnet dating in skarns. So that might be a better tool than carbonate.
All right. Thank you. So it seems we don't have more questions. So we would like once again to thank you, Catherine, so much for this very nice presentation, very nice talk. You can see Rafael saying best talk so far.
I agree.
And I like it very much. And so thank you. I hope you enjoyed talking with us today, and hope we can hear from you again in the future, in other talks and so on.
Yeah, definitely. I can talk about metamorphic rocks too. So maybe next time we can do some ductile deformation.
Let's work it on. Let's work on this. So,
Great.
So thank you. Obrigado, pessoal.
Well, thank you for inviting me. It was really great.
Obrigado a todo mundo que está presente na palestra hoje. Eu agradeço a presença de todos e cuidem-se. Tchau, tchau. So, thank you. Bye-bye. Take care.
Bye-bye. Thank you, Catherine.
We're gonna end right
bye.
now. Bye-bye.
Bye-bye.